The example one, the alternating harmonic series, 1 minus 1/2 plus 1/3 minus 1/4 plus ellipsis to the sum from n equals 1 to infinity of -1 to the power n minus 1 over n satisfies number 1. B sub n plus 1 is less than b sub n because 1 over n plus 1 is less than 1 over n. Number 2, the limit as n approaches infinity of b sub n equals the limit as n approaches infinity of 1 over n equals 0. So the series is convergent by the alternating series. Figure 2 in the sidebar illustrates example 1 by showing the graphs of the terms a sub n equals -1 to the power n minus 1 over n and the partial sum s sub n. Notice how the values of s sub n zigzag across the limiting value, which appears to be about 0.7. In fact, it can be proved that the exact sum of the series is the natural log of 2, which is approximately 0.693. See exercise 36. Example 2. The series, the sum from n equals 1 to infinity of -1 to the power n of, restarting example 2. The series, the sum from n equals 1 to infinity of -1 to the power n times 3n over 4n minus 1 is alternating, but the limit as n approaches infinity of b sub n equals the limit as n approaches infinity of 3n over 4n minus 1 equals the limit as n approaches infinity of 3 over 4 minus 1 over n, which equals 3/4. So condition 2 is not satisfied. Instead, we look at the limit of the nth term of the series. The limit as n approaches infinity of a sub n equals the limit as n approaches infinity of -1 to the n power times 3n over 4n minus 1. This limit does not exist, so the series diverges by the test for divergence. Example 3. The series, the sum from n equals 1 to infinity of -1 to the power n plus 1 times n squared over n cubed plus 1 for convergence or divergence. Solution: the given series is alternating, so we try to verify conditions 1 and 2 of the alternating series test. Unlike the situation in example 1, it is not obvious that the sequence given by b sub n equals n squared over n cubed plus 1 is decreasing. However, if we consider the related function f of x equals x squared over x cubed plus 1, we find that f prime of x equals x open 2 minus x cubed close over open x cubed plus 1 close squared. Since we are considering only positive x, we see that f prime of x is less than 0 if 2 minus x cubed is less than 0. That is, x is greater than the cube root of 2. Thus f is decreasing on the interval open the cube root of 2 to infinity close. This means that f of n plus 1 is less than f of n, and therefore b sub n plus 1 is less than b sub n when n is greater than or equal to 2. The inequality b sub 2 is less than b sub 1 can be verified directly, but all that really matters is that the sequence open bracket b sub n close bracket is eventually decreasing. Condition 2 is readily verified. The limit as n approaches infinity of b sub n equals the limit as n approaches infinity of n squared over n cubed plus 1 equals the limit as n approaches infinity of 1 over n over 1 plus 1 over n cubed equals 0. Thus, the given series is convergent by the alternating series test. Sidebar. Instead of verifying condition 1 of the alternating series test by computing a derivative, we could verify that b sub n plus 1 is less than b sub n directly by using the technique of solution 1 in example 11.1.13.